Yes, it is possible to reconfigure a 120/240 volt single-phase generator to provide a three-phase output. A single-phase generator typically has three stator windings, also known as coils, that are connected to the generator's output. In a three-phase generator, the windings are connected differently to create a rotating magnetic field that induces a three-phase voltage output. By reconfiguring the windings, it is possible to change the generator's output from single-phase to three-phase. To achieve this, the shipyard would need to firstly disconnect the existing single-phase windings from the output terminals, secondly, rewire the windings to create a three-phase connection. This involves connecting the three windings in a specific pattern that creates a rotating magnetic field, and thirdly, reconfigure the excitation system to generate a rotating magnetic field that matches the rewiring scheme. While possible, there are some limitations to this approach. The output capacity of the generator may be reduced when reconfigured to three-phase. The voltage regulation of the generator may not be as good as a purpose-built three-phase generator. The efficiency of the generator may be slightly lower than a three-phase generator. It is important to note that this reconfiguration should be performed by a qualified electrician and should not be taken lightly. Incorrect wiring or connections can result in damage to the generator or other electrical equipment. Let's delve deeper into the specifics of how this reconfiguration works. Understanding the original configuration of the single-phase generator is crucial. Typically, in a 120/240 volt single-phase generator, the three stator windings are connected in such a way as to provide two voltage options. There's a center tap which creates the 120 volts output, while the full winding provides the 240 volts output. This arrangement is common in residential and light commercial applications where both 120 volts and 240 volts are needed. To convert this to a three-phase system, the windings must be disconnected from the single-phase configuration and reconnected in a delta or Y configuration, which are the standard configurations for three-phase systems. The delta configuration connects the windings in a closed loop, with each winding connected to the next. This provides a balanced three-phase output. The Y configuration connects one end of each winding to a common neutral point, with the other end serving as the phase outputs. The choice between delta and Y depends on the specific application and the desired voltage levels. The rewiring process is not simply a matter of reconnecting wires. It requires a thorough understanding of the generator's internal wiring and the principles of three-phase power. The electrician must carefully identify each winding and connect them in the correct sequence to achieve the desired phase rotation. Incorrect wiring can lead to imbalances, overheating, and potential damage to the generator and connected equipment. Once the windings are rewired, the excitation system must be adjusted to match the new configuration. The excitation system is responsible for creating the magnetic field that induces voltage in the stator windings. In a single-phase generator, the excitation system is designed to produce a magnetic field that is synchronized with the single-phase current. In a three-phase generator, the excitation system must produce a rotating magnetic field that is synchronized with the three-phase currents. This may require changes to the exciter windings, the automatic voltage regulator, or other components of the excitation system. It is also important to consider the limitations of this approach. As mentioned earlier, the output capacity of the generator may be reduced. This is because the windings were originally designed for single-phase operation, and they may not be able to handle the high currents associated with three-phase operation. The voltage regulation may also be affected. Voltage regulation refers to the generator's ability to maintain a constant output voltage under varying load conditions. Single-phase generators typically have good voltage regulation because the load is evenly distributed across the windings. In a three-phase system, the load may be unbalanced, which can lead to voltage fluctuations. The efficiency of the generator may also be slightly lower. Efficiency refers to the percentage of input power that is converted to output power. Single-phase generators are typically more efficient than three-phase generators because they have fewer losses associated with circulating currents. When a single-phase generator is reconfigured to three-phase, these losses may increase, resulting in a slight decrease in efficiency. Despite these limitations, reconfiguring a single-phase generator to three-phase can be a viable option in certain situations. For example, if a vessel already has a single-phase generator and needs to add three-phase equipment, it may be more cost-effective to reconfigure the existing generator than to purchase a new three-phase generator. However, it is crucial to carefully evaluate the limitations and ensure that the reconfigured generator can meet the demands of the three-phase equipment. It is also essential to use qualified electricians who have experience with generator rewiring. They can properly assess the generator's capabilities, perform the rewiring correctly, and ensure that the excitation system is properly adjusted. In addition to the technical aspects, it is important to consider the safety implications of this reconfiguration. Incorrect wiring can create hazardous conditions such as electrical shocks and fires. It is essential to follow all applicable electrical codes and safety standards during the rewiring process. Furthermore, it is important to properly label the reconfigured generator to indicate that it has been modified and to specify the new three-phase voltage and current ratings. This will help to prevent confusion and ensure that the generator is used safely and effectively. In summary, reconfiguring a 120/240 volt single-phase generator to three-phase is possible, but it requires careful planning, skilled execution, and a thorough understanding of the limitations. It is not a task to be taken lightly, and it should only be performed by qualified electricians who have experience with generator rewiring. By following these guidelines, it is possible to safely and effectively convert a single-phase generator to three-phase and meet the power demands of a variety of applications. Let's examine the implications for the specific scenario described, which involves a vessel undergoing repairs and the need to power motors larger than 15 horsepower, which generally require three-phase power. The port engineers claim that the 12 wires from the generator have been configured to give a three-phase output without changing the nameplates raises several red flags. While it is technically feasible to rewire a single-phase generator for three-phase operation, several factors must be considered to ensure safe and reliable operation. Firstly, the generator's original design and capacity must be carefully evaluated. Single-phase generators are typically designed with different winding configurations and cooling systems compared to three-phase generators. Attempting to draw three-phase power from a generator not designed for it can lead to overheating, reduced efficiency, and premature failure. Secondly, the rewiring process itself must be executed with precision. Converting a single-phase generator to three-phase requires a complete understanding of the generator's internal wiring and the principles of three-phase power. Improperly connected windings can result in voltage imbalances, circulating currents, and potential damage to both the generator and the connected equipment. Thirdly, the excitation system must be reconfigured to match the new three-phase output. The excitation system is responsible for regulating the generator's voltage and frequency. Without proper adjustment, the generator may not be able to maintain stable voltage and frequency under varying load conditions. Fourthly, the generator's nameplate information must be updated to reflect the new three-phase output. This is crucial for safety and compliance with electrical codes. The nameplate should clearly indicate the new voltage, current, and power ratings of the generator. In the absence of updated nameplate information, there is a risk of overloading the generator and damaging connected equipment. In the case of the vessel, the fact that the port engineer did not bother to change the nameplate suggests a lack of attention to detail and a potential disregard for safety. It is highly advisable to verify the port engineer's claim by conducting a thorough inspection of the generator's wiring and testing its output with appropriate measuring instruments. If the generator has indeed been rewired for three-phase operation, it is essential to ensure that the rewiring was performed correctly, the excitation system has been properly adjusted, and the nameplate information has been updated. If there is any doubt about the generator's capabilities or safety, it is best to consult with a qualified electrical engineer or generator specialist. They can perform a comprehensive assessment of the generator and provide recommendations for safe and reliable operation. Ultimately, the goal is to ensure that the vessel's electrical system is safe, reliable, and capable of meeting the demands of the onboard equipment. Cutting corners or relying on unsubstantiated claims can lead to serious consequences, including equipment damage, electrical hazards, and potential injuries. Therefore, it is always prudent to err on the side of caution and seek expert advice when dealing with complex electrical systems. Let's also consider the potential impact on the vessel's overall electrical system. If the single-phase generator is being used to power both single-phase and three-phase loads, the rewiring process could affect the performance of the single-phase loads. It is important to ensure that the single-phase loads are still properly powered and protected after the rewiring. Additionally, the introduction of three-phase power could require changes to the vessel's electrical distribution system. This may involve adding new circuit breakers, wiring, and other components to accommodate the three-phase loads. It is also important to ensure that the vessel's grounding system is properly configured to handle the three-phase power. A properly designed grounding system is essential for safety and for preventing electrical noise from interfering with sensitive electronic equipment. Furthermore, the addition of three-phase motors could have an impact on the vessel's power quality. Three-phase motors can generate harmonic currents, which can distort the voltage waveform and cause problems with other electrical equipment. To mitigate the effects of harmonic currents, it may be necessary to install harmonic filters or other power quality improvement devices. In addition to the technical considerations, it is important to comply with all applicable regulations and standards. Marine electrical systems are subject to stringent regulations designed to ensure safety and prevent pollution. These regulations may specify requirements for generator installations, wiring, grounding, and other aspects of the electrical system. It is essential to be familiar with these regulations and to ensure that the vessel's electrical system complies with them. Failure to comply with applicable regulations can result in fines, delays, and even the grounding of the vessel. In conclusion, the decision to reconfigure a single-phase generator for three-phase operation on a vessel should be made carefully, taking into account all of the technical, safety, and regulatory considerations. It is not a simple task, and it should only be performed by qualified professionals who have the necessary expertise and experience. By following these guidelines, it is possible to safely and reliably provide three-phase power on a vessel without compromising the performance of the existing electrical system. The information provided by the port engineer should be thoroughly verified, and any doubts or concerns should be addressed before proceeding with the rewiring process. Remember that electrical safety is paramount, and it is always better to err on the side of caution when dealing with complex electrical systems. Finally, let's discuss some of the testing and verification procedures that should be performed after the generator has been rewired. These procedures are essential for ensuring that the generator is operating correctly and safely. Firstly, the generator's output voltage and frequency should be measured with a calibrated multimeter and frequency counter. The voltage should be within the specified range for the three-phase system, and the frequency should be stable and close to the nominal value, typically 60 Hz. Secondly, the phase rotation of the generator should be checked with a phase rotation meter. The phase rotation should be correct for the intended application, typically a BC or CBA. Incorrect phase rotation can cause motors to run in the wrong direction or can damage connected equipment. Thirdly, the generator's voltage balance should be checked by measuring the voltage between each pair of phases. The voltages should be balanced, with no significant differences between the phases. Imbalances can indicate a wiring problem or a faulty winding. Fourthly, the generator's load capacity should be tested by gradually increasing the load and monitoring the voltage and current. The generator should be able to handle the expected load without overheating or experiencing excessive voltage drop. Fifthly, the generator's automatic voltage regulator, or AVR, should be tested to ensure that it is properly regulating the voltage. The AVR should maintain a stable voltage under varying load conditions. Sixthly, the generator's protective devices, such as circuit breakers and fuses, should be tested to ensure that they are functioning correctly. The protective devices should trip in the event of an overload or short circuit. Seventhly, the generator's grounding system should be inspected to ensure that it is properly connected and provides a low impedance path to ground. A properly grounded system is essential for safety and for preventing electrical noise. In addition to these electrical tests, the generator's mechanical components should also be inspected. This includes checking the engine's oil level, coolant level, and fuel level. The generator's air filter should also be inspected and cleaned or replaced as necessary. The generator should also be visually inspected for any signs of damage, such as loose wires, cracked insulation, or corroded terminals. Any problems that are found should be corrected before the generator is put into service. Finally, a record of all testing and verification procedures should be kept, including the date, time, and results of each test. This record can be used to track the generator's performance over time and to identify any potential problems early on. In summary, a thorough testing and verification procedure is essential for ensuring that a rewired generator is operating correctly and safely. These procedures should be performed by qualified professionals who have the necessary expertise and equipment. By following these guidelines, it is possible to minimize the risk of electrical hazards and to ensure that the generator provides reliable power for the vessel.